Welcome to my session. That was a very long day, I do recognize that, and that's the final session. And it's actually an advanced SD-WAN session, so brave souls. Anyway, jokes aside, the session title is Cisco SD-WAN Hidden Complexity Revealed, How Cisco Attack Addresses Really Tricky Problems. And from the title itself, you can easily say three things. First of all, I'm from tech. The second one, we are going to have a technical deep dive. And the third one, that should help you to address so-called tricky problems. And tricky problems really comes from either lack of knowledge or lack of tools or both. So we will have everything of this today. And that's a second revision of that particular presentation. I've delivered the first one last year. Anyone from the last year who saw that presentation? No? Cool. Because you will have all the new stuff. So to be honest, if someone will tell me probably 5 years ago if that information will be shared across the public, and that definitely will change my life on a daily basis, because this is probably the very first time we doing an effort to go very deep in certain aspects of the SD-WAN solutions, specifically how edge device decides which path to use to forward traffic. We have all kind of policies, we have all kind of different configurations which influence that process, but we are never explain how it works. And that's the part of that presentation I really jealous you in certain way, because this is something really crucial for better understanding. So, and let me briefly introduce myself. My name is Denis Kodintsev. I'm a technical leader in SD-WAN tech team based in Krakow, Poland. In that current position, I'm working for the past 2 years. I'm in industry since, for the past 25 years, and Cisco since 2007. So I was doing different roles and different technologies, including very crazy one like phase synchronization for my mobile service providers, or broadband aggregation, or SDA at some point of my time. But the last 8 years I was doing primarily SD-WAN. So a little bit about housekeeping. I will do my best to secure some time for questions in the end of the session. But in any case, I will be there after the session for another 10 to 15 minutes, so you can come back to me and ask whatever questions you like. You can also join the web space available to you. You just go to the session catalog, select the session, join the discussion, and you will be in the web space with myself, and I will be able to address your questions. I will be monitoring that web space for the next 2 weeks up until the end of February. So for the agenda, it's pretty straightforward. What we're going to do first, we will try to set the stage and set the scope of that discussion, because we can really go either way. We can go to controllers, we can go to edge devices, we can explore different processes running on different platforms. So we really need to be laser focused on that. And also we need to, I need to set proper expectations for that session. But then we will explore how those topics we want to investigate are really covered with existing well-known tools available to you today. And those tools are really the same tools we're using in tech each day when we're trying to solve your problem as soon as possible. But the final part is crucial, because once we identify the blind spots, we will deep dive into those blind spots to really explain how it works and why it works that way. So let's move on. I'd like to set the proper expectations for the session. As I said, that's advanced session for SD-WAN. That means there will be no basic explanation how SD-WAN works. what are the features of the SD-WAN, how control plane established, how data plane established, how we exchange different policies. Nothing like that. So if you were expecting that, I have some bad news for you. You're in the wrong room. Okay? So with that said, we still need to be a little bit more specific because we cannot really go everywhere. We need to be more specific on some part of the solution. And the most crucial part, I believe, is the forwarding. And what really does the forwarding is the edge routers. Edge routers, which really takes the customer network and forwards the traffic across the overlay to other sites. So what we know about the edge routers, what they do normally. So they took some configurations and policies from all the different kinds of controllers, from vManage, which we call now as a manager, or from vSmart, which we call a controller as of now. And it applies those configurations and expected to forward the traffic according to those configurations. That's the configuration part of the story. The second part, and we might think we really know that part really well, how exactly we apply those configurations and how that any edge device really takes that configuration and translates it into something meaningful. But we will see there's something more on that. Also, from the control plane perspective, what we really know about the control plane, we have DTLS or TLS tunnels, which interconnects all our controllers, but also interconnects edge devices to controllers. But what we don't really know, what are additional hidden functions of those control plane tunnels, which we're mostly not aware. So we know OMP is running on top of control plane tunnels. We know netconf is used from vManage to edge devices to really forward the configuration. But that's pretty much it we know. And the final part, what we know about the forwarding, how exactly each device selects the tunnel it needs to forward specific packet or flow. So we know the policy we configure. So we know the tunnels is running on the device, which are probably operational or not, compliant with certain SLA classes or not. So how exactly that device is really able to select dynamically in a real time which tunnel to forward that specific traffic. And this is also a blind spot. We'll be focusing on the blind spots across that session. So what are these blind spots I'm referring to? From the control plane perspective, we will take a look on which you probably think you know quite well, which is DTLS or TLS tunnels. And these are, we think, just a transport, right? It's tunnels which interconnects our edge device to all the controllers. And then we have OMP session or netconf session, which runs on top of it, right? Not really. At least not exactly. There are some other aspects of that control plane tunnels, and we will dig deep into that. There's also policy or configuration changes. So we really know how to troubleshoot configuration changes coming from vManage perspective. So we can go, let's say we have a error message coming from vManage saying, okay, I cannot really apply that template. And you have some kind of error. You can go to vManage server log on the vManage itself, and it will tell you something. But what is the missing part? We're missing the respective part from edge device. What edge device is really doing whenever it tries to get that configuration and applies it. And the final part is really the one I think is the most important part of that presentation is the forwarding. How exactly average router builds the forwarding table according to existing policies, according to state of BFD tunnel, BFD sessions, and correlates all of this in a near real time. So every each packet, when it comes to the edge device, will be processed accordingly, according to your expectations. So these are blind spots. So we're just kind of assuming it works, and that's it. We don't really know how it works. So we will explore that. And the first part will be, okay, maybe we already have all the tools we need to really explore those blind spots. So let's take a look on these major tools we are constantly using in tech, and these tools are also available for all of you as well. So I will start with a very important tool, I would say crucial tool for control plane, which is called btrace or binary trace. You've heard of it multiple times from different places, from different speakers, but I really want to kind of specify the scope of the tool, what you can use it for, and what is out of scope. So first of all, what is it? Just a kind of brief explanation. So whenever we run a control plane, we have a bunch of different control plane processes, which might be BGP process or OMP process or SD-WAN specific process, which makes some specific stuff about forwarding or about tunnel management, whatever it is, doesn't matter. If we want extensive logging on that process, it will not be there by default. You really need to enable it. And it's not just a debug something message you tend to use in all days with iOS XE. There are specific message we need to run, a specific command we need to run to enable those debugs for a specific process. The good part, those logs are very extensive. They can provide you pretty much everything what's going on with specific process. So and this is the important part, the trade-off of that approach, you really need to understand which process to look. That's point number one. And the point number two, you really need to understand what to expect. Because if you have a lot of data and a lot of events, unless you understand if those events are really expected or not, that will not make any difference for you, right? So how can you enable those debugs? It's just a refresher for you, for those who are not familiar with btrace. And there are two different flavors. First of all, because we make some changes along the way with different versions. And before the version 17.10, we were using notation like debug platform software, SD-WAN. And then we just mention a specific process we want to troubleshoot. Once we do that, we will collect in the background, of course. We will not drop all the data in your console or terminal, no way, because it will be overwhelmed. But after release 17.10, we are starting to move slowly in a different notation how we enable btrace. And this is the set platform software. It's a little bit different notation, the same meaning. In the end of the day, and if you select the process of interest, and if you run that debug for that process, you can check the internals of that debug messages by show login process command. Why I'm saying that? Because from the SD-WAN perspective, you can run it for pretty much every control plane process relevant to SD-WAN. But the problem is the same. Unless you know which process to look for, and you understand how to translate those outputs into something, in some insights or something meaningful, that might be a challenge for you. So the rule of thumb recommendation, so whenever you're on a learning curve, you are kind of exploring what's really happening in the background. And this is another aspect of this kind of debugs, because you can really you can run those debugs pretty safely. They are not affecting control plane or data plane to a major extent, so you can run it for pretty much any process with some cautious, of course, but nevertheless. But what you can do, you can run it not just for one single process, but for all SD-WAN related processes at once. And by doing so, you collect all the data related to SD-WAN. And then you take that data, you take it offline, you analyze it, you check what is the call flow, is it matching your expectations or your understanding of the process, and then you can do some actions on that. So the challenge with btrace, again, it will show you the result. It will show you how different processes works, but it doesn't tell you why it works that way. So you really need to have that knowledge, and I will try to bridge some gaps for that knowledge for you today. The other tools, two tools I'm going to cover really brief, is the packet trace and WPI. These are primarily specifically related to data plane. It has nothing to do to the control plane. Btrace for the control plane, packet trace and WPI for data plane only. Essentially what packet trace does, so whenever we apply configuration to device and policy, that configuration and policy translates in a set, and not just set, but actually a sequence of features applied and programmed in the data plane. So whenever a packet comes in, there is a pre-built sequence for each potential flow. So whenever we need to select a feature, it's already there. So data plane can easily forward the traffic between the features, so it will not introduce any meaningful delay or performance drop. So from that perspective, it really gives you a very good opportunity to understand what's going on whenever we are forwarding traffic across one single device, because you're running that on one single device. And the easiest way to run it is just use those commands. You can really use ACL, for instance, just to highlight the traffic of interest, the source and destination, all the ports you like, but the easiest way is just to use one IP address, either destination or source. All the traffic which is really including that IP address, either as destination or source, will be captured. But not the traffic itself, decisions the router makes upon forwarding that traffic. And how it looks like. So there are two different aspects of that. Some features, and we will have a list. We will have a list of features applied to every packet. From the very beginning, once the packet comes into the router, once we see the incoming interface, to the very end, when we decide which encapsulation to use and which outgoing interface to use. But what it really missing sometimes, it really missing crucial information because it doesn't really tell you why it choose specific path or tunnel or interface. It gives you some ideas. You can really try to translate it, but unless you have a deeper knowledge, you will be struggling with that. And sometimes we can really find, from SD-WAN perspective, we can really find very useful information like, okay, we do see that traffic was classified as ICMP. And we also see that based on the policy, we actually going to load balance that traffic across all available tunnels towards destination. And for that specific flow, we selected that specific tunnel. That's very good because it will tell us a lot, but not all. Moving forward to WPI, what is not good about the packet trace? It's local, so you cannot really run across the entire network end to end, and it really doesn't tell you why we're making those decisions. WPI makes it a little bit better because you can run that feature end to end. So what it really means, and again, it's primarily for data plane. When you want to understand how traffic moves across your network within average device, and if there is an issue, what kind of issue you are seeing, and what, and potentially why. When I say potentially, because what is really happening? Whenever you no longer need to configure it from the CLI. You go to vmanage, you go to NWPI, which is network-wide path inside. You make a statement which kind of traffic you want to chase, and then what vmanage does, it goes to each device along the way and says to that device, okay, this is type of traffic I'm going to monitor. So whenever you see any traffic of that, please let me know. What are you doing with that traffic? So whenever traffic comes in a first hop device, the first hop device using so-called radioactive tracing, we're adding a special metadata label to that traffic. And along the way, when other devices sees the same traffic, it's those devices seeing that metadata. Once they see that, they instantly know they need to report all the decisions they made around that packet to the vManage. So what it gives us, it gives us opportunity to really collect all the data across the path of the forwarding path to the vManage, and vManage can really correlate it in a kind of single end-to-end picture. So if there is issues out there, and what kind of issues, in a certain way, it also provides a packet trace functionality inside vManage UI. But in a kind of light version. It will not tell you every each step we are doing on whenever we processing traffic, but it will tell you a lot of, in a digestible, I would say, way, but not all of that. The challenge with NWPI is the same. It tells you what it's doing, but not why. So we are really close to the point when we are going to cover those blind spots. And let's kind of summarize the blind spots with the tools. So we want to explore configuration management, control plane, around DTLS, and forwarding plane. So what btrace is missing from, as I said, we really need to understand what to expect from a specific process to really translate it into something meaningful and understand if the issue we're seeing is really because it's unexpected, or because we did some misconfiguration or make some false assumptions somewhere. For the packet trace, I think the most important challenge is, I'm probably reiterating myself, but that's a crucial part. We know exactly what's happening, but we don't really know why. And the same challenge with the NWPI. We really go end to end, but we are still missing why part. So let's explore those blind spots around control plane, configuration management, and the forwarding plane. So with a focus on, we will start with DTLS and configuration changes, but before that, I'd like to remind you the general architecture of the control plane of the every each SD-WAN router. Every each SD-WAN router nowadays is running IO6C operation system. But it also runs a set of processes which were added to IO6C once we apply those functionalities, SD-WAN functionalities to SD-WAN routers. That had happened a few years ago. The important part from that architecture is following. So first of all, we have iOS, and it's still there. We are using iOS for multiple reasons. We are using that for building a routing table to run specific routing protocols which we don't really need to implement, like BGP or SPF, which we run on a service side. We also use iOS for SSH session or different types of services like DHCP, which is totally fine. We just add some additional functionality with processes which are specific to SD-WAN. There is also important part from the forwarding plane. So whenever we build a routing table, and I will cover that a little bit more in the next slides, we actually supposed to translate that routing table into the forwarding table. So our data plane, our router on the hardware level, should be able to take that structure, take that data, and use it instantly without consulting back to the routing table or policy we're using. It just needs a data structure to have a packet comes in and instantly decide which encapsulation to use and which outgoing interface to use. And for this, we have a pair of processes, which is called FMAN. They always go in pairs, FMAN FP and FMAN RP. FMAN RP is, you can think of it that way. So this is a single process which stands two legs in two different domains, I would say. So FMAN RP stands in the control plane domain. It's universal IO6C which runs on top of every each router. But we know exactly that every each physical router runs different hardware. And we need a respective part of the same process, which is FMAN FP over here, which basically a bridge to that hardware. It translates the commands from their universal control plane to specific data plane. Okay? And again, we have a bunch of processes on the SD-WAN part. What I'd like to say about the SD-WAN processes, just for reference, for your reference, we have multiple of them. We'll be focusing only on a few of them today. Primarily, we'll be talking about FTM, which is Forwarding Table Manager. This is the one which builds forwarding table for OMP routes. So whenever we need to build the forwarding table, which we are using on the data plane, this is the one is responsible for that. We also have other different processes, some like OMP. Everybody knows, I hope everybody knows OMP. And we also have something which is not very widely known, like vDaemon, for an instance. What is it? We will figure it out in a second. So let's start with vDaemon. What is it and what's this all about? So vDaemon is primarily related to DTLS or TLS control plane tunnels. So why is that? Let me briefly remind you how control plane tunnels are established and what you might be missing from that picture. So first of all, the very first step is to initiate connection from edge device to the vBond. And that would be a DTLS tunnel, which is created by that edge device. Then vBond will provide some data. It will provide NAT or PAT configuration. It will provide number of controllers and credentials for those controllers, basically IP addresses for vManage and vSmart controllers. Then we just establish different control plane tunnels, either DTLS or TLS, and run different protocols on top of it. This is something you're supposed to know by now. And we run, let's say, NetConf towards vManage, or we run OMP towards vSmart controllers. This is how it worked. And there is something crucial, because it's mentioned sometimes, but maybe I can ask a question for all of you. Have you heard of something which is called equilibrium state for control plane in SD-WAN? Anyone? Okay, cool. That's good. So the way you can think of it, it's basically the balance state. So every each device, including controllers and edge devices, have a certain expectations on the number of control plane connections which should be running. So it knows how many controllers are there. So it knows how many control plane connections should be up. And it tries to reach that balance state, which is called equilibrium state. Unless it reaches that state, it will keep connection to vBond. You all know, normally we just turn down the connection to vBond, but it's not the case. We actually keep in that connection until we really create that equilibrium state. So, okay, we've reached that equilibrium state with one vManage and two vSmarts, and we turn down that connection. Now we can really reestablish that connection if something changed. But here's the trick. How that device really knows if something changed on the control plane perspective. It doesn't have connection to vBond anymore. OMP doesn't provide that information. NetConf doesn't provide that information. Where it comes from? It actually comes from the lightweight protocol which runs besides OMP and NetConf, which we call viptela primitives. We are not often talking about that for different reasons. But this is really important to understand. So basically, there is additional protocol, lightweight protocol, which exchanged on top of DTLS or TLS tunnels, and that helps to device to understand if it's in equilibrium state or not. If it sees that the number of connections, control plane connections of its peer, let's say vManage or vSmart, or edge device itself, different comparing to that device, it will go to vBond again. This is a triggering event for that. Now, how it works in the background. This is where vDaemon process really comes in. vDaemon process runs on an average edge device and also runs on average controller. This is the process which builds the DTLS or TLS tunnels. It starts on the vDaemon process and it ends on the vDaemon process on the other side. But it also introduces something very important. You all aware and heard of system IP, right? I guess. Some of you might think of system IP as some kind of router ID, but it's really it's really IP address of a specific interface. But you don't really see that interface anywhere because it's really hidden. It really resides in a dedicated VRF or VPN table running on average controller or an average router, and there is system IP interface. What it basically allows for vDaemon to really provide a transport for all different processes like OAMP, convd, on top of DTLS tunnel. So all of these processes included vDaemon bind to that particular IP address, system IP address. And that allows those processes to communicate to each other controller with system IP across control plane connections. This also includes that lightweight protocol I've mentioned before. So what's important for you from that? You can run btrace commands for vDaemon specifically, and that will allow you to really understand if there is some issues on reaching equilibrium state for the control plane. The second part is really that you sometimes can see the difference that vManage tells me, okay, vManage sees only 2 vSmarts or only 1 vSmart while I'm expecting 2 vSmarts. Maybe I need to go to vBond and double check if there is something changed over time. And easy way to think of vDaemon and how it works with the system IP in place. I think everybody who actually operates SD-WAN solution sees or tries to establish a SSH connection from vManage UI to remote device, either vSmart controller or edge device. And you will have SSH session in your UI. What really happens in the background? We are establishing session from system IP on vManage to system IP either vSmart or edge device across DTLS tunnel. So vDaemon is a crucial part on having those DTLS tunnels and reaching equilibrium state for that. So what to look for on vDaemon operations? So first of all, if you see that edge device keeping connection to vBond, this is not expected. Because normally, if device reaches equilibrium state, it should turn down that connection. That's a clear indication that device is unable to reach that state. So you really need to check which control connections are up and running and why you're really missing something. Some connections are missing. The second one is a little bit different. You can really find that the connection to vBond comes down and up again, and it basically flaps. That might be an indication or even bigger problem in the background, because it could really happen because the controller out there sends new information. Okay, I'm vManage. I'm saying to you, I have a different set of controllers connected to me. And edge device really receives that information, sees the difference with what the information it has, goes to vBond, double checks, sees there's no change, and it drops the connection to vBond again. But then vManage comes back again and says the same. Okay, I have a different set of controllers connected to me. And that keeps running. And this is really can give you an indication that something goes wrong in the background. So a little bit of configuration part. The crucial process for how edge device takes the configurations from the remote, from the vManage is process named confd. How it actually works? There is a lot of different components in vManage, but I really want to kind of emphasize on the major process itself. So what really happens? So you start applying a device template. That device template goes through different stages in vManage. vManage, what is really doing? It takes that change you want to apply. It takes the running configuration from the device. It compares those two configurations. It calculates the difference, and it applies that configuration across either RESTconf or netconf protocol. The difference, either it's RESTconf or netconf, it really depends on the release. In the later releases, we're using RESTconf, and the way we encode the changes, either XML or JSON. So normally you can really run some debugs on the vManage side, but normally you don't really know how to do that from the edge perspective. So we know for sure what to look for when we cannot really apply configuration from vManage. For an instance, that could be vManage server.log. But there is a different part of the story. Whenever we apply that configuration from vManage to device, what is really happening on device? So you can really understand that and apply it in your workflow. So vManage is really not pushing configuration anymore, at least from the 17.6.x or 20.6 versions. What it does, it notifies the device that there is a new configuration available to you. So please come back to me and pull that configuration from me. So then device initiate in some point of time a REST API call, go to the vManage, ask for that new configuration, takes that configuration and then apply it. If applying that configuration was successful, it will report to vManage that everything went fine, and you will see a green indication in vManage. Okay? So how can you check that from the edge device perspective? So first of all, the easy one. You can run command show sd1 config pool history, and you will see all pool entries, so all the occasions when device reach out to vManage to check that and to check that information. Okay, and sometimes, let's say you try to apply the configuration, but vManage tells you, okay, I cannot really apply that configuration because there is an error coming from device. You can really go to device and check it a little bit further, and you finally realize, okay, I have a bad CLI error. And that bad CLI is saying, okay, I cannot really apply configuration to interface gigabit 002. And the reason for that, because I don't have that interface. So your template could have an interface which is not existent on actual device. And you cannot understand that from vManage perspective. You need to go to the device itself. So there is a different aspect to confd process, because we're not just receiving configuration or templates from vManage. We're also receiving policies, both localized and centralized. And we have beat races to really run to understand what's going on whenever something goes wrong. With that, we really come to the very last part of our presentation, which is, I believe, crucial part, the forwarding. How exactly each edge router decides which path, which tunnel to take for each packet. So we'll start on a high level, and the easier one. Whenever a packet comes in from the tunnel, it's pretty straightforward. We don't really need to kind of dig deeper, because what we have is really, we're taking the packets, we checking the interface implicit or explicit ACL, we do a lookup, then we decrypt the packet, we understand it's for us, then we need to understand to which VPN we need to forward that packet based on the label associated with that packet. And finally, once that packet went to a specific VRF, we just do a regular lookup, IP lookup, nothing else. That's pretty straightforward, nothing fancy here. But it's completely different when we see that from the outgoing direction, when we send traffic from the LAN side to the overlay, to the prefix which is learned over OMP. The difference is we're starting with the very basic stuff, which is also pretty straightforward. ACLs, lookups, classification with ANBAR. Then we run our policies. We're really making some decisions. Okay, which SLA class we should match, or which interface we should prefer. But then something strange kicks in, like OC walk. What is it? What OC stands for? This is basically the moment when device decides which path to take, which tunnel to take, based on all the information it gets from the previous stages of the forwarding. And we will go deep into that. So, but before moving forward, I'd like to kind of recap on something now real quick, just to be on the same page. So what is a RIP, or routing information base? That's essentially a routing table. Everybody knows that. There is a different aspect to that, which is FIP, or forwarding information base, which is normally is just a data structure which is built based on the routing table. But we are creating that data structure the way, so whenever we need to process a specific packet, we can instantly say which interface to take for outgoing direction and which encapsulation we need to attach to that packet. Normally, whenever we run a non-SD-WAN solution, we will be using IPsec for that. IPsec builds the forwarding information base for non-SD-WAN solution, but it has nothing to do with SD-WAN. It knows nothing about application aware routing. It knows nothing about our data policies, or SLI classes, or BFD states. So for that matter, we have so-called output chain elements. This is the name of forwarding information base for SD-WAN. This is specifically designed for Cisco SD-WAN. This is not something which is widely known or used. And I will explain explicitly how it works and why it works that way. If you would ask me which slide, one single slide to take from that presentation to really explain it on a high level how it works, that would probably that slide. So we start with multiple processes which is running in the control plane, an SD-WAN control plane. And we need to build our BFD sessions on top of IPsec tunnels. That's the first step. So how it really works? We build our sessions towards remote location, remote and tunnel endpoints. We are receiving data from OMP as a TLOC routes. Those TLOC routes processed by tunnel table manager and then forwarded to FTM process. FTM, again, that's the one who builds our forwarding table, which we are using on data plane. But it also uses, again, when I said we are reusing iOS XC very often in SD-WAN, there is a good reason for that. We don't really need to invent the wheel. If we have a good infrastructure within iOS XC to build IPsec sessions, we are going to use that. This is why FTM really goes to iOS and says, okay, can you please build IPsec session for me? This is the IP encryption keys. You don't need IKV2. You can use encryption keys I've got from TTM, from OMP. So IPsec in iOS really takes that information and builds IPsec tunnel on the data plane. On the other hand, FTM doesn't need any help on building BFD sessions and on top of IPsec tunnels. So it builds itself. Now we build our IPsec tunnel and BFD session, and the next step would be, okay, we are getting two different types of routes, both from LAN side and from the OMP perspective. And we combine those routes in the combined routing table. And this is where we are also using iOS. iOS is very good solution to really calculate the best routes from different protocols in the same place. And then we provide that information to FTM. And that's the moment which is completely confusing for most of the people when they realize that. Because we have two different sources to build the forwarding plane in SD-WAN router. For routes coming from the LAN side, either connected or let's say BGP or SPF, iOS will build those forwarding tables with IPsec itself and propagate those routes into the forwarding table and program the data plane. But for the routes coming from OMP, FTM will take those routes from the routing table and will calculate the forwarding table and will program the data plane specifically for SD-WAN routes. So we have a kind of two different processes which builds combined forwarding table. And the distinction between them is either those routes coming from OMP or they are locally originated. So there are different btrace debugs you can run. This is mostly for your reference. You can run those btraces because this is the control plane. This is not really about the data plane yet. We are just building the tables. There is a different aspect to that because iOS is not really involved in building BFD sessions. Whenever you run show BFD summary command, which is OK for autonomous mode, you will see nothing, 0 BFD sessions, because iOS knows nothing about BFD. All BFD sessions are really created on the FTM level, and only FTM knows about that. So if you want to debug failing or inconsistent or unstable BFD sessions, these are commands you need to run for btrace for FTMD. So let's connect the dots, how SD-WAN OC really works. And I've decided to go a little bit different way this time, and that's an important one. So let's design our SD-WAN feed from the scratch ourselves. So what we are really expecting from the forwarding information base or forwarding table created by FTM. We need to provide ECMP load balancing. So we have multiple tunnels. We're expecting to be able to forward the traffic across all those tunnels on per flow basis, which is totally makes sense. We also understand we have different type of policies like data policies, application-aware routing policies. So we really need to be able to select with those policies specific tunnels or remote or local endpoints. So we need with a policy to influence our selection process. We also need to provide support for application-aware routing. So whenever BFD session sees that specific tunnel is not compliant with our SLA class, we need somehow to influence our decision process, forwarding process, based on that information. We also need to support service chaining, which we are using for service chaining labels for that. And more to that, whenever there is a change, we don't really want to recalculate the entire forwarding table. There's no way how we can recalculate our forwarding table over and over again entirely. So can we really do that with IPsec? Probably the first part that's the only part we can really do with IPsec, nothing else. But so let's think what option is. So if we will think the way how IPsec works. So it takes the prefix. So the prefix we are looking for is destination prefix over there. We have multiple tunnels connected from our sourcing device to the destination. And we have a table. We are trying to build a structure around. So we have destination prefix. So what we can start with? We can start with something which is very similar to IPsec. So we need to decide on outgoing interface, which is in our terminology is a local TLOC, tunnel endpoints. And we need to decide on encapsulation, which tunnel to take. So basically, whenever we need to forward the traffic across IPsec tunnel, we just decide on specific IPsec tunnel, and from that we know for sure which header we need to add to that specific packet. What's good about it? So we can easily do the load. We can really do the load balancing, and we can dynamically reroute the traffic if some tunnels will fail. And we actually can select some tunnels by the policy. We can just we can remove some tunnels from the forwarding table. And sounds good? looks like a solution for us. But there are some cons to that. So first of all, with that approach, we cannot really prefer specific tunnels or T-locks. There's no way how we can really select with a data policy with that kind of structure. We cannot do SLA-based policy because it doesn't really recognize any changes from BFD. There's no way, there's no point in that structure which takes that information. And the most important part is whenever there is a change with a tunnel or prefix or local interface, the almost entire forwarding information base should be recalculated. And we don't really want that, because that will lead for constant recalculation over and over again. So how can we improve that? Okay, so if we want to prefer to have ability to select remote tunnel endpoints, let's say, in our case, this is 2 endpoints, 10.1.1 and 20.1.1. We can add an additional layer to our structure, which will allow us to influence that selection. Sounds good? Okay, it's much better. Now we can prefer remote TLOC, remote tunnel endpoints, but we're still missing application-aware routing, we're still missing service chaining, and almost every change will be translated to entire recalculation of the forwarding table. Okay, what we can do next? So we can change a little bit the structure which points to the remote tunnel endpoint, and add to that structure SLA class. For every SLA class we configure it, we can really have a set of T-locks which points to the tunnels compliant to that SLA class. Okay? And for every SLA class, and SLA class, just to remind you, SLA class 0 stands for all tunnels. So whenever you're not running any application or routing, every traffic will go into SLA class 0. Okay? So now we have application-aware routing. Now we can really prefer the remote TLOC, and we do support that, but we're still missing some parts. We cannot really prefer local TLOC. So if we want a policy which will prefer specific local interface, we still cannot do that. That structure doesn't support that. And we cannot really do service chaining as well. So as a second step, what we can do, we can add additional layer of the similar setup, but it will allow us to select not just remote TLOC and SLA class, but local tunnel endpoint and using SLA class. So the important part here, SLA class is not something we are choosing when we are going through that structure. It was chosen before with application routing policy, which happened before we reached that point. So whenever we go to that, we already know exactly which SLA class to match. And finally, if we need to enable that structure with service chain support, we know that service chain is really based on changing the label we include in the IPsec encapsulation. And this comes the final part of the puzzle. That's really the additional layer of structure, of the structure. But how it's different from this is what we built with just all of us, let's say. How it's different from the actual FIP we are running in SD-WAN. This is how it's different. Almost virtually no difference. And this is all just because we want to kind of match all those expectations, and we don't really want to recalculate the data each time we have a change. How the forwarding really works in our case. So we know, let's say we wanted to send traffic to that destination, and we know that we selected SLA 0. So the first step, we select SLA 0 class. Then we do see we have multiple labels, multiple pointers pointing to a next label. What basically means we can select any of them. We can do ECMP balancing over here. This is what we are doing. We just select one of these available tunnels, basically. And as the next step, we go to another stage of that forwarding, and we do the same. But in the first step, we selected remote tunnel endpoints. As a second step, we select local tunnel endpoints. And by selecting those two tunnel endpoints, what we're actually doing, we're selecting the specific tunnel we want to use. Okay? And that ends up in the specific interface we are going to use for that. So this happens each time for each packet on a per flow basis. This is really important. For the same flow, there will be the same path the forwarding will take. In the end of the day, we'll be using specific tunnel. So what really happened with that structure if something goes wrong? So let's say one of the remote TLOCs goes down. Okay, so that will be translated in some minor changes in our structure. So we will just remove anything related to that specific remote TLOC. That's it. We don't really need to recalculate it over and over again. If we, let's say, we have received OMP route delete from remote location, we will just remove associated structures. We will not affect anything related to the tunnels itself. If we will breach SLA class 1 on specific tunnel, the change will be very minor. This is tunnel 4, and the tunnel 4 is only selected in that particular place. And because it's SLA 1, we should expect only one single point we need to change. And this is what's really happening in the background. FTM, which is really processing all that information in a real time, doesn't really need to recalculate the entire structure. It really needs to be laser focused on those changes we apply. So I will skip that, but the most important part is really to give you how you can troubleshoot that and how you can use it on a daily basis before we will wrap up. So the first one, how the OC chain or SD-WAN people really looks like in real life. It's actually, it's not a list, it's not a linked list, because you have multiple tunnels, you have multiple paths you can take. So it's actually a tree. So whenever you create or FTM creates a structure for you on that, you actually have a tree on that. So how do you trace that? And why would you trace that? Because whenever you see something is not expecting with the forwarding, you really want to know if the forwarding plane matches your configuration. And that's basically the only way how you can confirm that. But because we are building that forwarding plane in FTM and then propagates that forwarding table all the way to the data plane, we really need to check it on multiple stages of that. We need at least 2 stages. We need to check it on FTM, and this is quite easy. You just run one command, you just check the prefix you need, and there is a pointer to the next hop. Once you get that pointer and run that command, you will have FTM perspective on that particular OCA chain or forwarding table created by FTM. But this has nothing to do what really happened in the data plane, because FTM supposed to kind of program that data plane. What is really happening in the data plane is a different story. You really need to go step by step, connecting the dots, following the same path from the very beginning, from the prefix itself, and you will see, so every step will be having a hash value, which is pointing to the next step. And you just kind of following that path step by step, and you sometimes will see, okay, now I see the label I'm using, which is 1003. Then I will see which tunnel which SLA class I'm choosing, actually, and which tunnel is eventually I'm choosing for forwarding that specific traffic. By following one by one, you really understand how it works. So what to look for with that? So first of all, you really want to make sure by checking those OC chains with those commands, and you will be able to check those commands in the presentation I will share. You don't really want to see any broken chains. What broken chain means? That you have a pointer which points to nowhere. This is totally not expected. You should be looking for that. Every chain should end up in a tunnel, period. The next part is missing path. You sometimes can see that, okay, I cannot really forward the traffic across specific tunnel, and I already above my session, I'll probably take 1 or 2 minutes to wrap up, and then I will take questions if you like. So you will be looking for missing path, missing tunnels from that equation, but also you can check additional path you are not expecting to see. Sometimes you will see 4 different tunnels in the OC chain instead of expected 1. And this is totally not expected. You just want to really find that discrepancy and investigate it. Unless you look into that OC chain, you won't be able to identify that. So, and finally, because you have different perspectives from different processes like FTM and data plane, you can really compare those 2 different perspectives and really understand if something is broken, when exactly it was broken and where. So, and you actually can use that information in the tools you're using on a daily basis. For the packet trace, you can really see a lot of new data you previously just discarded. Now you see the SLA class. Now you see the tunnel ID. Now you see the label. You understand what's going on with that. And you really translated the information on a completely different level, that knowledge I've shared with you today. And to wrap up, key takeaways and calls to action. So first of all, an obvious one. Learn what is expected and what is not. Unless you know that, unless you learn that, you cannot really have any insights if what you see is an issue or expected behavior. This is something obvious. Also, if you need to choose one single tool to troubleshoot control plane, btrace the tool of choice. If you need to troubleshoot your data plane, use NWPI, because it will give you end-to-end visibility. Be aware of the control plane lightweight protocol, which is run on top of vDaemon, because it will affect your equilibrium control plane state, and it could lead to unexpected behaviors around those control plane tunnels. This is very crucial and important and not really covered anywhere. Know exactly when to go from vManager and troubleshooting your configuration changes to the actual device and how to troubleshoot them. So I've provided that information for you as well. And now you know the most kept secret about how forwarding works on CH device. How we actually build that forwarding table we're using in real time, and how we can really update that forwarding table without ruining our control plane, essentially. And this is where FTM process kicks in, and this is all the structure I've shared with you really helps. So again, I'm reminding you, you can join the session WebEx space to ask the questions. I really encourage you. I will appreciate your feedback on that session. I'd really like to understand what else you would like to see and more detailed deep dives I will be doing probably next time. But also, I really want to understand if it's something you want to see, that kind of information or deep dives on a regular basis. Other than that, please continue your education, and also I can recommend 2 sessions. One session I will have tomorrow morning, and I will go through 7 specific case studies, and I will explain how you can really go into real troubles when you do false assumptions with Cisco SD-WAN. Another part is around NBAR, which will be happening on Friday, run by my colleague Louis. If you want to know more about traffic classification or application classification, that's the session to go. With that said, thank you very much for staying so long. I hope that was informative for you. I really appreciate your feedback. And if you have some questions, please reach out to me through the WebEx space, and I will be here for the next 10 to 15 minutes to take your questions.